In the second example of the discrete event simulation case study, we will look at the APIs, the programming interfaces of the core libraries and how they are used. So we've seen in the last unit that the class wire and the functions inverter, AND gate, and OR gate represent a small description language for digital circuits. What we need to do now is we need to give an implementation of the class wire and these functions which allow us to simulate circuits. And those implementations in turn are based on a simple API for discrete event simulation, which we are going to study first. So what is discrete event simulation? A discrete event simulator performs actions which are specified by the user to take place at a given moment. An action is simply a function that doesn't take any parameters and which returns unit. So everything an action it does by its side effect. And the time when an action takes place is simulated. It has nothing to do with the actual wall clock time, it is the simulated time. So concretely, we are going to write simulations inside objects that inherit from a trait called simulation. And that trait has the following signature. There is a function current time, which returns the current simulated time in the form of an integer. Then there's a function after delay, where the user can install a block of statements to be performed as an action at a time that is delay time units after the current time. And finally, there's the function run, which lets the user start the simulation and execute all installed actions until no further actions remain. So let's take a look at the structure of a typical simulation application. It would be composed of several classes that are shown in this class diagram. At the top of the diagram you have the trait simulation, which we have just seen in its API. That trait would give you the necessary tools to do any kind of discrete event simulation. That trait would be inherited by something that is a little bit more special, namely that gives you the tools to do basic circuit simulation. In particular, it would contain the class wire and the gates for AND, OR, and inverter. They would be defined on this level here. One level further down, you would have a trait that gives you more complex circuits, call it circuits. And here you would find things like the half adder and the adder. And then finally, you would have the concrete objects that the user wants to simulate. Call this maybe my simulation. So that would typically be an object that can obtain all the functionality in discrete event simulation, the gates and the circuits, by inheriting from these traits. So that's the structure of a typical application. We have already seen simulation. Let's look at the interface of this gates layer next. So in the gates layer, you first have the class of wires. To be simulated, a wire should support three basic operations. The first operation is get signal. That should return the current value of the signal that's transported by the wire. Current means at the current simulated time. Then there should be a way to change the signal of a wire. That's done by the method setSignal. That modifies the value of the signal that's transported by the wire. And finally, there's a third method called add action, which lets us add an action to be performed every time the signal of a wire changes. Here the idea would be when the signal of a wire changes, then certain things should happen. The things that should happen can be installed, so to speak, with a call to add action. So here's an implementation of these ideas for wires. So a wire then would have a private variable sigval, which is the value of the current signal in the wire. And it would have also a private variable actions, which are the actions to be performed when that signal changes. getSignal simply returns sigval. The setSignal method would take a new signal value. If it's different from the old one, the current signal value is updated and all actions are executed. So that's done by calling the forEach method on each action, and what is being done is that the action is simply run by applying it to the unit parameter. If we use a for loop for the same signification, we would write it like this. So that would expand into exactly this code over here. For A, taken from action, run A. The last method is called addAction, and what it simply does is it prefixes the current action to all the actions that are already stored in the wire. And what it also does, that turns out to be technically necessary to get the simulation off the ground, is once we add an action, we immediately perform it a first time, because otherwise it turns out that the simulation would essentially rest in an inert state forever. So we have to perform the action a first time to get things off the ground. So to summarize, the state of a wire is modeled by two variables, sigval, which represents the current value of the signal, and actions, that represents the actions that are currently attached to the wire. So once we have wires, we can look at gates. Let's look at the inverter first. So the inverter is implemented by installing an action on its input wire. That way, that action would be performed each time the input wire changes. And what would the action do? Well, it would produce the inverse of the input signal, but not immediately, but only after a certain delay. Call that inverter delay units of simulated time. So that's the idea. Let's see how that would be put in code. Here's the inverter method. It takes an input wire and an output wire. And here's the inversion action. So what to invert the input wire, what we would do is we would take the signal of the input wire, and then we would set the output to the negation of the input signal, but we would do that only after a certain delay. So we use this method from the simulation API after delay. It says perform this block here, inverted delay time units after the current time. So that's the invert action, and this action should be performed every time the input wire changes its signal. So we achieve that by adding this invert action to the input wire. So that way the wire itself would perform this action every time its signal changes. The AND gate is implemented in a similar way. The action of the AND gate then would produce the AND, the conjunction of the input signals of the output wires, and it would happen after a certain delay, call it AND gate delay, units of simulated time. So that gives us the following implementation here. AND gate takes two inputs and one output. The AND action, we take the values of the two input signal. After AND gate delay, we set the output to the logical AND of the two values of the input signals. And when should this action be performed? Well, it should be performed anytime the signal of one of the two input wires changes. So we add that AND action to both input 1 and input 2. That way we are sure that whenever one of the two input changes, the output signal will be recomputed. As to the OR gate, that's implemented quite analogously to the AND gate. So here you still see the AND gate. To go to the OR gate, we simply change the action in OR action from the logical conjunction to the logical disjunction, the OR of the two input signals, and otherwise everything is exactly as in the AND gate. So to test your understanding, let's have a look at the way these signals are computed. So we take the get signal for input 1 and input 2 before we run the code in after delay in a separate val definition. So the question to you is, what happens if we compute the two signals in 1sig and in 2sig in line? That means inside the after delay call instead of before writing them in value definitions. Would the new definition of OR gate, call it OR gate 2, have the same behavior as the previous one, or would OR gate 2 not model OR gates faithfully? So let's analyze what would happen. In the new program, once an input signal changes, we would wait OR gate delay time units and then set the output to the disjunction of the sampled two signals. But the sampling would take place at the time after OR gate delay, and the output change and the sampling would appear at exactly the same time. In the original OR gate, of course, we would sample first, then wait OR gate delay time units, and then set the output afterwards. So you have seen that it does make a big difference whether the signals are computed outside after delay or inside, and consequently OR gate 2 does not model OR gates faithfully.